Alright, welcome to video number 2 of lecture 18. We just talked about the geothermal resource, focusing on high temperature regions. Now we're going to talk about how we would extract energy from a high temperature region. So as a reminder, this is the ground, and there's some sort of rock, we'll call it a cap rock, which water cannot pass through. Below that rock, we have some water in the water table, or water existing in rocks that are porous. And below that, we have a hot spot, or some local magma that has penetrated into the Earth's crust and is really close to the surface. So that magma is heating this water in the water table, which gets really hot and could or could not be as existing as steam or really hot water in the Earth's crust. So what we're going to do is we're going to drill and we're going to extract that steam or hot water, and we're going to use it. So we're going to learn about 3 systems that we can use to extract this, and then we're also going to learn about one new method we can use to access more steam. Alright, so system number 1. This is the most basic and most economical. It is the dry steam power plant. The word dry is so misleading. Whenever we say dry, we mean not wet. In other words, the steam is all vapor. There is no liquid. So let me show you how we're going to use this. All right, so we have 2 wells. We have below this well some trapped steam, and in one well we're going to extract that steam, and it comes out. So this is high temperature, high pressure steam, and we're just going to put that straight into a turbine. You remember the Rankine cycle? We're going to do the Rankine cycle, but we've removed a few components. We'll discuss that in a second. So we're going to put that steam directly into a turbine and allow that steam to expand. So here we have hot steam, high pressure, high temperature. It reaches here, and we now allow it to expand. We're increasing the volume it exists in. Its pressure is dropping, and it's doing work on our turbine. It's going to exit our turbine still as steam, but now it is a saturated steam, so it's almost about to start turning back into liquid water. Okay, so you would say, well, let's just put that right back into the ground, but we're going to do something even better. We're going to run that steam through a heat exchanger. My lines are a little off. There we go. Okay, so this right here is a heat exchanger, which we will call the condenser. And what that condenser does is it exchanges heat in the steam with water that is passing through a cooling tower. So we have water that's entering the cooling tower, and it is generally cold, or at least somewhat close to evaporating. So it's cold, and it enters, and it's going to come in here. Now, here, leaving the turbine, we have saturated steam. So it's hot, but it's on the verge of turning into a liquid. And what the saturated steam is going to do is it's going to transfer heat into the water, the colder water that is now running next to it, so that by the time we leave, we have now condensed liquid water, which we put right back into the ground. And so this water in the cooling tower is going to pass right by our hot steam, and it will eventually evaporate and turn into a fairly low quality steam. So it's just some steam and some water, and it's going to be allowed to escape into the atmosphere. Whenever you pass a power plant, you see large towers with a lot of smoke coming out. It's really steam coming off the cooling towers. Okay, so we allowed our steam. Sorry about that. Okay, so where were we? Yes. Let's see. Okay, so we have a heat exchanger, which is condensing the water, turning it back into, this is now a liquid water, which we pump back into the earth, and then we allow some steam to take away the excess heat. And the question is, why do we condense the steam? Why not just put this steam directly back into the earth? Okay, well, the reason we do that is because the steam, when it's condensed, so what the condenser does is turn steam, which takes up a lot of volume per unit mass, into liquid, which doesn't take up very much volume per unit mass. Imagine how much steam you would get from evaporating a little bit of water. So what that does is that really decreases the amount of volume this water is taking up, and it creates a suction effect that's pulling more steam through. If we just allow this to exhaust to the atmosphere or into the ground, then our back pressure, or the pressure on the other end of our turbine, would be much higher than if we allow the steam to condense, which draws more steam through the turbine and increases the amount of power we get out of our system. So condenser turns steam into liquid, which sucks steam through the system. We don't need to pump this thing because there's already highly pressurized liquid here, right? So we don't need a pump. We also don't need a boiler. So this is just like the Rankine cycle, but both the boiler and the pump are the ground. So the ground, the earth, does the job of both adding heat and compressing our liquid into either a vapor or a compressed liquid. Okay, so these systems are great because they are simple, plus they're economical, right? You can imagine this won't cost very much. The fuel's free. However, it only has about a 20% efficiency because we can't get as high of a pressure of steam as we need to really extract a lot of work. The pressure won't be as high as you'll run in a standard coal-fired power plant or a combined cycle power plant. So you can't extract as much work because there's not as much potential there. Okay, and then regarding how much steam, a 55 megawatt plant will require about 100 kilograms per second of steam. And that's quite a bit. Okay, and finally, what I forgot to mention is you use this kind of plant when you have dry, clean steam. In other words, you have pure steam without liquid in it, no liquid water, and it's clean, so there's no particulates or other gases that you... If you have other gases, it will increase the back pressure of your turbine. So if you have nitrogen in there, and what that will do is decrease the amount of power you get out. Okay, so that was system number 1. Let's talk about system number 2. All right, and that is a single flash power plant. Sounds like the natives are at the door trying to get in. 1 second. Okay, so a single flash steam power plant is going to look very similar to the last one, with a few differences. Okay, there's our ground. Okay, we're going to pull out steam from our hot reservoir like we did before, but now there's a difference, and this is the main reason we would use this, is we're using this when our field, our geothermal field, produces wet steam, which is a vapor-liquid mixture. So we don't have pure steam, so we can't put that straight into a turbine. That would not be good. So instead, first, we allow the hot liquid to enter this expansion valve. And what that does is it flashes some of the hot water into steam. So we've got, I'm going to draw it as blue for now because it's a liquid, but we've got this hot liquid entering our system, and it's pressurized to the pressure of the reservoir, so it remains at the same pressure the whole time. But then once it enters this area, it flashes, so there's a lower pressure as it enters, and that causes some of the water to become vapor to fill the space. And so now we have a somewhat high pressure vapor, not as high as a pressure as our last system. And we're going to, just like before, expand that in a turbine. And that extracts shaft work, which we can turn into electricity. And then, just like before, we have a condenser, which is really just a heat exchanger, exchanging heat with a cooling tower, where cold water enters and a steam water mixture leaves. So that is our waste heat. Our heat in is like right here, and we are getting some work out right here. This is our moderately high pressure steam, which leaves as a saturated vapor, and then it exchanges heat to turn back into a saturated liquid, which we then put right back into the ground. Okay, and the cooling tower starts off with moderately cold fluid, which we then turn into steam, and that evaporates off. Okay, so that is how a single flash power plant works. The main difference, right, is our field is producing wet steam, so we can't just put it straight into a turbine, which must have only vapor. Okay, and the kind of special thing is our liquid is flashed in an expansion nozzle. Essentially, we just take some given amount of steam contained in a certain volume, and then we expand that volume all of a sudden, causing some of that liquid to turn into steam. Okay. Again, we are cooling the steam here to create suction, as the steam, which takes up a lot of volume, is shrunk down to a liquid that pulls more steam through this turbine, dropping the pressure at the end of the turbine, creating more power. Okay, it is less efficient since we get even less pressure out of our steam going into the turbine, so less efficient than system number one. It's also a little bit more costly and requires a little bit more steam, but nonetheless used because having the ideal resource for this system one, this perfect steam, very hard to come by. All right, that brings us to system number 3. These are kind of in order of what type of resource you have. So this is called a binary cycle. All right, now we're going to look at the situation when our steam, which is wet steam, so it's liquid plus vapor, is contaminated, right? The ground is not this perfect storage vessel. It's filled with other gases we don't really want in there, that won't condense in the turbine, etc. So when we have things in there that we either can't put through a turbine or that will impact the performance, then what we're going to do is we're going to put an ORC, organic Rankine cycle, on top of a heat exchanger, exchanging heat with the ground and our working fluid. So how this works now is we have a closed loop with the ground. So the fluid coming in from our hot reservoir, so here's our kind of Q in. We've got some fluid that's moving through this pipe and then goes right back in. It never really leaves this pipe, just goes in and out. There's some sort of pump, obviously, on this system to move that fluid. I'm sorry, I neglected to say, on a single flash power plant, we do need a pump generally in order to move the fluid, because we're keeping this fluid at the pressure of the reservoir. Before a system number one, we didn't even need a pump, right? The steam is the pump. Here we needed a pump. Here we need two pumps, actually. One pump to move our closed loop cycle, which goes through this heat exchanger, which for all intensive purposes we will call the boiler. Kind of modeling this after a Rankine cycle. And so that boiler then is the boiler of a standard Rankine cycle. So we have a boiler going into a turbine, and then leaving we go into a condenser, which exchanges heat with a cooling tower, just like in our last two examples. And that goes into, another pump that's used to circulate the fluid in this Rankine cycle. So you see we have a closed loop here, and leaving this heat exchanger is going to be hot, high pressure steam that we evaporated here in this heat exchanger, the boiler. Then that steam expands in the turbine, dropping its pressure, becoming a saturated vapor here before that heat leaves and it's turned back into a liquid, transferring that heat into the working fluid of the cooling tower so that that heat is ultimately rejected as Q out. Then our pump increases the pressure of our fluid to keep it moving in a cycle. And then we exchange heat with the hot fluid coming out of our reservoir, which gives its energy to our organic Rankine cycle and then goes back into the ground. And that heat is ultimately replenished by the heat coming from the earth. Okay, so that's an organic Rankine cycle on top of just a heat exchanger acting as our boiler. That's a binary cycle. We call it an organic Rankine cycle because flowing through our Rankine cycle is not water but isobutane. That's our working fluid. And we do this because it has a lower boiling point, so we don't need as high of temperatures. So the temperature here can be somewhat low and still evaporate this fluid here, which is what we need to happen in order to have a high pressure steam, or sorry, just vapor here, isobutane vapor, which we expand in this turbine to get work out. All right, that is a binary cycle. Finally, I'm going to tell you about one process that's interesting. It has a few different names. The name I will use because it's the one people want to use now is enhanced geothermal systems. Okay, so let's say we have some geothermal plant, which is maybe it was in the past we didn't always put liquid back into reservoirs. In fact, only 70% of plants put the liquid back into a reservoir. Some of them still export that for processes or something. So what we've done is we have expended our supply of steam. We have a heated area, but there's no more steam in there to use. So what we do is we get a very heavy duty pump and we pump some high pressure liquid into there. And we allow that to enter all the little cracks in the earth. And we're doing that because around the steam supply are more steam supplies that are trapped by caprock. So this high pressure fluid creates fissures between these reservoirs, And once we've created a fissure, steam is once again allowed to enter, fill this area, and we can once again run our cycle. So this really is fracking for geothermal. And it's still being developed, not used too often, but I'm sure it will be as we kind of begin expending various resources. All right, that's the technology that we use for high temperature electricity generation of geothermal resources.